Hello there, everyone. We are back in the social science lab today. Just a reminder that I'm not going to cover every point in these video lectures, so I'm going to try to make them quick. Excuse me. I'm not going to cover things that you could just read on these PowerPoint slides, for example. Chapter 5, Atmospheric Pressure, Winds, and Circulation Patterns. Well, you could have just read that, right? So, this is actually a great image, because you could see some tropical storms that may become hurricanes if they keep on building. And if you look over North America, kind of by Minnesota, that looks like a tropical storm that is kind of dissipating, kind of thinning out as it moves over land. All right, so we start looking at atmospheric pressure, right? In a nutshell, that's the pressure from the air on top of us, right? The air on top of us has mass. It feels very light, sure, but it has an overall mass. So if a storm system comes over you, that could change the pressure. Or if you're in a vehicle and you go up an airplane, or you go down into a valley, your ears will pop, right? You'll feel that pressure change. So why does it matter? Well, understanding pressure is a part to understanding the weather and air circulation patterns. So hot air rises, right? That's why a hot air balloon goes up. Well, in general, when hot air rises, let's say it's rising right above you, well, that's low pressure, right? That hot air is rising, going up. Things that are heated tend to expand, right? Including the air. And because it's expanding, there's less of it directly over you. So the pressure goes down. But if, let's say you have a warm front above you and a cold front comes on in, that's opposite pattern, right? That'll create a higher pressure system. And something else I want to point out, you see the word cyclone here. In general, sometimes cyclones are referred to the same as a tropical storm or a hurricane. But technically, that converging air and air rising is called a cyclone, and it does not have to be a storm. Okay? There's a little bit in there about wind power. I think it's pretty cool, but I'm not going to go into it right now. So isobars, right? Showing you got an H for high pressure and an L for low pressure, right? And you see that you have a steep gradient and a shallow gradient. Basically, it's just like looking at, maps that are showing gradients of altitude of a mountain, let's say. It's a similar principle. That line has the same value going all the way around it. We'll talk more about this in a minute. Something else to understand when you're looking at storms and why they go where they go and do what they do is the Coriolis effect, right? The atmosphere on the Earth is affected by the Earth spinning, right? So in a nutshell, because of the spin and the shape of the Earth being circular, things to the north of the equator, and things in the atmosphere primarily, will move to the right, and things south of the equator will move to the left. This could include a lot of different things, not just wind, but ocean currents, whatnot. I'll show you some examples in a little bit here. So this here is a picture of Hurricane Katrina. Very big storm. Look at that huge, massive storm. It's a good example of a hurricane and the power behind a hurricane. Lots of damage. So when they're looking at Hurricane Katrina and trying to predict, well, where's this thing going to go? Knowing the Coriolis effect, that things on the Earth's surface, including storms, turn to the right, that helps you figure out where it's going to go. Unfortunately, there's all kinds of other things that go into where it's going to go. What exactly is the temperature? What's the temperature of neighboring by systems? Which direction are other wind flows going? As you can see, when a hurricane goes over land, it tends to get smaller and slow down. So that's why it's kind of smaller down there over Florida and over those islands where the water is less deep. And then when it goes above land there, it also shrinks again. And as you can see, it gets its biggest over the deepest water, right? Because that's where it gets its power from, the water and the heat. All right, little bit more about the Coriolis effect. Well, I'll just read this stuff, look at these images. So besides storms, as you can see, prevailing ocean patterns. Again, north of the equator, you see things going around to the right, and south of the equator, you'll see it going around to the left. This is a little track of Hurricane Katrina again to show you basically the pattern it took. Now, when the hurricane is over the ocean, it's going to do more of a turn because it can flow more freely over the ocean than over land. That's why when it's over land there, it kind of straightens out a bit. So what are some ingredients that go into hurricane? Well, you need warm water energy, right? This is why we don't see hurricanes as much in the winter, but they do happen sometimes. You need low wind shear. What does that mean? Well, wind shear are winds that come in and will mix up that storm, make it so it can't keep on building and building on top of itself, right? And because of the Coriolis effect and the storm spinning, that's the reason why it's able to keep that energy in that smaller area. So it builds it up straight high up into the sky, right? And sometimes these storms will just stay over the ocean, just kind of hovering for a little bit as they're building before they hit land. So the Coriolis effect is very weak around the equator. That's why the area around the equator we call the doldrums. Rain and storms that happen around the equator are usually just kind of intermittent, not very powerful, not like a hurricane. This is some more Hurricane Katrina damage. You could read this stuff on your own. So some more things about winds. Winds are named after their source. What does that mean? Well, that just means where they're coming from. So as an example, easterly winds. If something's called an easterly, you better believe it comes from the east, right? And as you see on this island here, you have windward and leeward winds. The reason this is important is because windward, you'll tend to have your rain, right? Is that water is pushed up. When I say water, I mean moisture in the air is pushed up. It precipitates out, right? The air can't hold that water anymore as it gets colder. Think of it like a sponge. The atmosphere is kind of like a sponge. As it gets colder, it's like you're squeezing the sponge and wringing it out, and precipitation has to come out. That's good for there. So, some more examples. Excuse me while I get a little bit of water. So, these temperature, air change differences happen regularly over day and night over areas like this. So remember, as a general rule, water heats up and cools off more slowly than the land. So, for example, during the day, the sun's out, right? It's getting hot, so the land is heating up quicker than the water, right? So because that land is heating up more quickly, that air will start to rise. And basically colder air, the air that is over the water, will be sucked up there behind it. And the opposite thing happens at the night. And you can see a similar thing happens in mountain chains. This is another really good example of how, when that air mass, when that wind is hitting a mountain, you'll get all your rain, or maybe not all of it, depending on the size of the mountain and different altitudes. But you'll get a bunch of rain on one side, and the other side could be very, very, very dry. In fact, that wind coming down can be so warm and so dry as it's coming down that it can become a huge hazard. As in the Santa Ana winds, and every year we always hear the news stories about all those fires. Alright, I'm reaching 10 minutes, so I'm going to turn this off and start again.